Okay, so it's good and weird to be back. So I left here about 365 days ago, give it or take one day. So my presentation is about spotting and safe concurrent Ruby patterns. And who am I? My name is Ivo Anjo, as Raul said. I'm a Ruby lover. When I joined Talkdesk, I had written maybe 20 lines of Ruby before, but I really enjoyed working in it for almost 3 years. So I became a really big fan. I'm also a concurrency lover, and so I'm a JRuby lover, which probably is not news to the people who know me, but for those of you that don't, yay. So I'm currently working at the Amazon Profiler team, which is an internal product I cannot tell you anything about. So yeah, cool. Which is cool, but it's a cool product. And previously I was here. So what we mean about when we say concurrency? We mean dealing with multiple things during the same overlapping time period. So that's the gist overall description of it. And Ruby has several concurrency primitives. There are several tools in Ruby for you to run several things at the same time. One of them is threads, the other is fibers, and the other is processes. So because each of these you can do like 10, 20, 100 presentations on each of them, I'll focus on threads, which is my favorite way of solving some of the hardest problems that we can get. And let's talk about how Ruby works in threads. So you might not be aware, but there's actually multiple Ruby implementations. The one that most people use is, or that most people call basically Ruby, is MRI Ruby. And the name comes from Matt, which is that lovely Japanese gentleman which created Ruby. And MRI means Matt's Ruby interpreter. Ruby is no longer an interpreter strictly, but there are other Ruby implementations. JRuby is very commonly used. Truffle Ruby is also up and coming, and Ruby News, nobody cares about this. I wish even the developers of Ruby News cared, but they really don't. I never got this to work on my computer, and I tried like 5 times over the past 4 years. It never built on my computer. So if they don't care, I don't really care. Also, fun story, Truffle Ruby, this logo was designed here at Talkdesk, so nice. And it was actually a nice story. Oh, here's the creator. She designed the logo. And the story was basically, I wanted to make a presentation about multiple Ruby implementations, and I was missing a logo. So I convinced people to do a logo, and they accepted. Okay, so all of these Ruby virtual machines support working concurrently, but only the ones at the bottom really support working in parallel. So what's the difference between both? The difference is that when you work in parallel, you do several things at the same time. So you can do 2 things at the same time in different threads. When you work only concurrently but not in parallel, you do one bit of one thing, then you work on something else, then you switch over, then you switch over. So this is the big difference between like the most used Ruby implementation and all of the others. So in any way, the issues that I describe here in this talk apply to all of the Rubies. So you can these learnings apply to all of the Rubies and probably to many other languages too. So it's relevant not only when you're doing really parallel stuff, because concurrency always finds a way to bite you. Who's using threads? It's quite common in the Ruby ecosystem. So things like web frameworks, web servers, message and processing queues, etc. All of these tools, which, if I remember well, many are still in use around here. Use threads, make use of concurrency. So that's why it's interesting to look into this, because either your code or one of your dependencies is already making use of this, or your dependencies are using threads to call your code. So you always need to be interested about what's really going on and find out how we can improve it. So why would you want to use concurrency using threads or concurrency in general? The main two reasons for me is to improve efficiency. So you can work, modern machines have many parallel resources, so you can use all of them to improve your requests and to work on them faster and to reduce latency. So if you have multiple things that you need to do in order to service some user requests, if you split them up into small things and you do them at the same time in parallel, you will reduce your latency and provide users with a better experience. So the meaty part of the talk is what should you be on the lookout for when you're working with concurrency. And all of these stories are based on true events. You can try to jot them out, and at the end you can ask me, oh, what was, you can try to guess which system we saw this. But yeah. So pattern number one, when you are using or equals to initialize things, this initialization is not atomic. So for instance, imagine that you have some database client or some singleton that you want to initialize, but you're using or equals to do it lazily because you don't want to slow down the startup of your application, or this only gets used sometimes, so you don't want to create this until you really need it. If, for instance, we're using this to create a new database connection, and we do it like this, what happens is if we're calling this code using multiple threads, is all your threads will try to connect to the database, especially if, for instance, you're restarting your service under load. And what will happen is that you'll create like multiple database clients where your objective was to create only one. And this can be good or bad or harmless, depends on your pattern. So you might overwhelm your database with new connections, so your database might just blow up. You might leak resources, so maybe your application after this keeps background memory and threads and things like that. And at some point in time, it will fail due to these resources still being there unexpectedly. And maybe it's not a database client. Maybe you're trying to lazily initialize some object that will create an email, trigger an alarm, do something else, and so you will get screwed. So let's try to fix this. So the classic solution for when you're using multiple threads and you have problems like this is to make it so that only one thread at a time is doing one of the things that is doing the thing that you want. So if you use a mutex in this case, you try to wrap your initialization with the mutex and maybe problem solved. Maybe. If we try it, it actually doesn't work. So why doesn't it work? So if I was to execute this very slowly, you will see that each thread would get here, it would check, oh, is the database client available? Oh, it's not. So it would actually proceed to try to grab the lock. Now, because we added the lock, only one thread will win, and the other 4 threads in my example will wait. But after the first thread is done initializing the client, all of the other threads will, one by one, grab the lock and create the new client. So this is why we haven't fixed it. This is why, even though we added the mutex, we still get like 5 different connections when we didn't want to. So the solution is that we need to check that other threads haven't gotten there first. So the trick is basically adding this part. So the idea here is that we grab the mutex and then we check, oh, is the database client already initialized? Because other threads might have gotten there first, we need to check if our decision is still the same. So that's the takeaway from here, is that when we do this, it works, and whoops, out of order, this one. The takeaway is be careful and always recheck your state when you're getting called by the mutex. So the idea of a mutex is you might reach some decision and you say, oh, this is what I want to do, and then you reach the mutex, you grab the mutex, and then between you grabbing the mutex and you actually executing, some things may happen, so you need to check again, oh, has the world changed? Is everyone still here? Am I ready to work or not? The other detail, which I jump over, is you need to be careful to not do things like this, which is you need to use the same mutex for all of the threads. Of course, a lot of these examples are very obvious when I pack them down to 4 lines, but if you have a big application, things may be modular and whatever, so it might not be entirely clear that this is actually happening. So you need to be careful. The idea of the mutex is that every thread that tries to grab the same mutex, only one of them will succeed. But it has to be the same one. So pattern number 2. Don't change and iterate hashes concurrently. So imagine that you have that you're doing some work in one thread which you are saving in a Ruby hash map. You're adding things to a hash map, and then in another thread you have the same hash map and you're trying to read it. So this simple code tries to do that. One thread writes to the hash map, the other thread tries to read it, and what happens is it fails. You get this error. Can't add a new key into hash during iteration. Actually, this error is a very good one, because this means that Ruby is actually protecting you. So something wrong may have happened, and Ruby actually says, no, I don't allow you to do this because otherwise it will break. So this breaks in the good way, which is in a very loud way, instead of silently, and you just corrupt your data, which is what other languages sometimes do. And Ruby also, but not in this specific case. So this one is a good one, but the problem is this jumps out in the example, not at all in production. So when you have this object, this hash that gets passed around like 5 different classes, and then one starts working on a background thread, and then you don't really know when this happens. It's actually, also it's one of those things that it's probabilistic. So some of these things only happen when the threads are all in the same very specific state. So it might happen that on your local test you never find many of these problems, because the very specific interleaving of one thread doing one thing and the other thread doing other thing might not actually happen on your test. But in production, your code gets hit like millions of times per day. So like that 1 in a million happens once a week or once a day or once an hour. So the solution for this one is you can avoid sharing. So as always, if you avoid sharing things between threads, or at least mutating one thread and reading in the other, you are always safe. If you use a persistent data structure that allows you to, at the same time, create a copy to change and access, is also a good solution. So these are like 2 solutions that you can use. The other solution is you can use a proper concurrent map that allows you to, at the same time, access it and modify it. So the concurrent Ruby gem gives you one such tool, the concurrent map. And so if you run this code with concurrent Ruby, it will work. Takeaways from this example. You should avoid mutating any shared object, not just hashes. So if you share things between all of your threads, you should really try to not modify them after you've shared them. So you create an object, you put things in there, and after you pass it on, it no longer gets modified. That's the best way to avoid any problems. Some of these things break only under production traffic, and this is the famous Heisenberg bugs that can take you days, weeks to catch, because they only happen in that specific setup that you cannot reproduce on your local machine until you find what specifically is happening. And also the concurrent Ruby gem is your friend. So if you really want to do things, fancy things, you should look into it. So pattern number 3. Thread local variables are actually thread global, which is quite unexpected to people that come to Ruby from Java, because in Java this does not behave like this. So let's imagine that you're using a tool called the thread local variable. So Ruby actually allows you to have a hash-like object that each thread gets a different copy of that object. So each thread that calls this code will get a new client. This is why this pattern or equals is safe, because only one thread, each thread will create its own copy, so they will never share an object, so it's okay. But imagine that you're using this to implement some object that you say, oh, I want this object to be thread safe, and each thread will get its own copy of some connection, and I'll just use my object. The problem with Ruby's thread local variables is that if you use like 2 copies of this object on the same thread, you actually get only 1 copy of the thread local variable. So here I'm trying to create a gateway for Google and for GitHub, and when I run the code, I get 2 gateways for Google. So what happens is that actually these variables that are thread local, they are, so each thread gets its own copy, but they are in essence thread global. So each inside each thread, each read of this variable will be the same read. So if you have multiple instances, it does not matter that you have multiple instances of this object, you always get the same connection. So this is why you need to be careful. So the solution is actually to use concurrent Ruby's thread local variable that gives you the behavior that you were probably expecting, which is that each thread gets a copy of the objects, but gets a new copy for each instance of these objects. So this way, we fix this code, and we can use 2 clients for different things on the same thread. So this one is pretty straightforward after you know it, but if you don't know it, it's one of those that might take you a bit to find. So the takeaways are the thread local variables from Ruby are actually a low-level mechanism. So we need to be careful when you're using it, or probably just avoid it. And just use concurrent Ruby's higher-level alternative. And let's go on to pattern number 4. And this is one of my favorites, because it's actually not entirely about concurrency, but it's one that's really hard to find. So spot the difference between like these 3 examples, this one, and this one. So lots of Ruby data structures allow you to initialize them with an object or a block. And this might look exactly the same, almost the same, but it's a world of difference in what you get. So for instance, if we look at the first one, let's say that we create an array with 5 elements of this hash. And then we change the first element of the array, and we print the array, and we find out that actually all of them changed. This is because Ruby did what you required of it. You told Ruby, hey Ruby, create a new array with 5 positions and put this object on those positions. And Ruby did. Ruby put that object that you create there 5 times on the array. So you get 5 copies. What you may have wanted is this, which is when you pass it as a block, Ruby actually calls your block 5 times. And so each time you create a new hash map, and then you save it on an array. And so when you change the first element, you only change the first element. So you get an array with 5 different objects instead of 5 times the same object, which is probably what you wanted. A very similar thing happens with the hash. When you create a new hash, you can pass in an argument. This argument is the default object. It's the argument that Ruby returns you when you try to access a key that's not there. So for instance, I try to access the key hello, it's not there, and so Ruby gives me my default object, and I put in that list world, and then same thing with foo. But then when I try to read it, you'll see that I get both objects on the same array. So this is again the same example. We passed in a single array instance to Ruby, and then Ruby used it as a default for all keys, but it's still the same. What we probably wanted was this. We wanted to pass it a block, which means that whenever Ruby needs, whenever you call the hash with a key that does not exist, Ruby will call into your block and give you a new copy of the array. So in this case, I add world to hello, I add foo to bar, and then when I print it, I get nothing. it's actually interesting why you would get nothing. And you get nothing because by default, Ruby does not associate the value that it returns with the key. So you need to do like some extra things there to save the object. So it means that each time you call #2 hello, you will get a new object for all of time. So why does this matter for concurrency? This matters because of our last example, which is actually one that I've seen like twice. Very helpfully, both times were during code review, so it never went in, but it's actually exactly the same problem. So I've told you, oh, you can use a thread local variable and you'll create a special object that every thread that calls it will get a copy. So when you do this and you pass in an object to the thread local variable, you're passing in the same object. So this is the same default object. That means that every thread that tries to read it, so we try to read it in 2 different threads, and then we create a new thread that tries to read again the thread local variable, and we find both values. So this was, again, probably not what we expected. And this one is especially evil because we were using thread local variables to make our code very concurrency fancy, and it broke. Whoops. So again, the solution is thread local variable allows you to pass in a block, and this gives you the behavior that you were expecting. So takeaways from this example. You need to be careful. When you pass in the default value by reference, you always get the same object. If it's an immutable object, like a frozen string or a number or some kind of other object that never changes, it's not a problem. If you expect to be mutating that object, you need to be careful. That might not be what you're expecting. When you pass a default value using a block, you get different objects unless you return an existing reference. So you can always, of course, inside your block, you can return whatever you want. So you can like create a variable before and pass in always the same variable, and then you landed on this case, and I don't know why you were doing that. So takeaways from this. Both of these cases are useful. You might want to use this in different cases, but you need to be careful. When you see this pattern, pause, look at it and check, okay, is this the right version that I want, or am I using the wrong version of the code? And when you're using the thread local variant, you need to be very careful. So pattern number 5. When you're loading stuff on Ruby, all of the definitions required, etc., that you might be doing are not atomic. So what does it mean? It means that, for instance, if I have this very simple class that has 2 methods, one that prints hello, one that prints goodbye, and then I slip 1 second between them because a definition is still Ruby code. So I'm running Ruby code while the class is getting loaded. What happens is I try to, for instance, load this class in a background thread and then start using it, is that I get an exception. Because in this case, I had 2 threads. One thread is loading the class and hasn't finished defining all of the class. And then I'm already creating new instances of the class. And I can still call hello. So hello gets printed. But because by was after our sleep, we had a slow load and we missed things. So this one is especially irritating because you see undefined method by, and then you go into your code and you see my method is here, and it found other methods. So why not this method? Because this is not atomic. So if you get multiple threads, like for instance, all of these cases are especially. These kinds of initializations are especially painful if you have a web server, you've just restarted your web server under loads, and at the same time you get like 30 requests at the same time, and your web server is racing to start things and load things, so you might be careful if you're not doing this correctly. Of course, this one is pretty obvious that you would never write something like this, but sometimes the frameworks write it for you. So you need to be careful. So solution is always require before use in the current thread. And as an alternative, you just require once at the beginning of your application, require everything, do not do anything lazily, and boom. So again, be careful while we're doing concurrency and lazy work. And Ruby's internal structures are thread safe, so it was not Ruby that broke. Ruby was cool. The internal structures are still very concise and have no problems, and they are very consistent, but your code is not. So sometimes due to the Ruby implementation, Ruby is safe, but your code is not. So you should not rely on Ruby to deal with some of the problems that you have. So pattern number 6, when you have a shared worker, interactor, or controller with state. So this is a very simple example. You have some worker class. The worker class has a call method. It saves as instance variables, like some 2 arguments, works, and then returns the sum of them. So if we try to execute this code, the same worker on 2 different threads, what we'll get is that usually both threads will return you the same value. Even though, if you see, both threads, you were supposed to get like 3 in one case and 7 in other, we'll see that both threads get the same result. Why? Again, because this is the same object. So both threads, like the first thread to get in, writes its own variables. The second overwrites them. So by the time that we're done, both threads are seeing the same values where they shouldn't. So of course, the solution for this is create another instance of your worker and have one instance per thread. So the important takeaway is, again, don't share objects and mutate the state at the same time. So this is the presentation. You can just burn this into your mind and go home. And objects are cheap, so be careful about over optimization. Oh, I don't want to create like this object. Okay, so you're creating 200 temporary objects, and you're trying to save one object that has like 20 lines of code and 2 instance variables. Don't do that. First, write your code to be correct, and then you optimize the places that need to. So, in general, how are we with time? Okay. In general, don't panic. I'm done with my patterns. Don't be afraid of this. Don't go home and say I'm just going to program like Haskell from now on. The key takeaways are use concurrent Ruby if you want to do concurrent stuff. It gets you all of the tools that you are expecting and that the Ruby standard library does not give you. I don't know why. I hope they give you one day. So thread pools, actors, channels, promises, etc., if you want to get really fancy. But one of the important things, which I actually missed here, is the thread safe data structures, like things that you can use and you pass around and they will know that they work under concurrency. It supports all of the fancy Rubies, and if you were thinking about, oh, but I don't want an extra dependency, it's a dependency of active support. So if you wrote a Ruby web something, it's already there. In some of your dependencies have already pulled active support. The other is do not mutate shared objects or use immutable data structures or persistent. So one example is this gem that I created, which is the persistent diamond gem that allows you to create like an immutable array, an immutable hash, an immutable set. And this can be fairly shared between threads. And obviously, when you cannot change them, you can only create a very efficient copy with the changes. So this is a very cheap way. And it also makes your code very pretty because you use emojis. And it works. It really works. Emojis in code, amazing. So the other key takeaway is when you use any of the alternative Ruby implementations, your threads are parallel, so you get faster concurrency. Hopefully Ruby 3.0 will soon be with us, and it will also bring this to the upstream Ruby under the form of guilds, which is a new concept that is being introduced. But while it's not, this is where the fun's at. Final, have fun. This kind of thing is all concurrency and threads and whatever also always seems like something that is really hard and leads to these very, very annoying whatever bugs. And so people just shy away. I would say just play with it, experiment with it, play with actors, play with different models, and you'll get it. I think if I can do it, I think you can get there, pretty sure. So that was my presentation. Thank you. I have a blog where I blog about things, and all of the code examples are up on GitLab because GitHub now belongs to Microsoft, so I moved it. And This one also? I moved everything. So that's it. Thank you, and questions. Oh. Questions? No one wants questions. No one wants to try to guess which systems on Talkdesk got bit by which one.
Actually, can you say more about the new stuff that's coming on 3.0?
On?
On 3.0?
Yeah. So I don't have slides for that. But the thing is, Koichi Sasada, which is one of the core Ruby developers, is proposing a new concept which is called guilds. Ruby guild is basically works as if it was a separate Ruby process. Or so each when you start your Ruby application, you will have only one guild, which is the default guild. Under that guild, you can have several threads and share things, and you'll still have exactly the same behavior as I said here. So it will be concurrent but not parallel, and you will have all of these problems. But the idea is that when you get to 3.0, you can create more guilds. So your application can say, I want to start another guild. When you start another guild, that guild can have more threads, but those threads can run in parallel with the threads from other guilds. So for each guild only allows you to be running one thread from that guild at a time, but different guilds can be running in parallel. So that's the one thing that allows you to run multiple threads. And the idea is also to be very limited in the way that you can communicate between guilds. So if you want, you cannot access objects from one guild to another unless they are immutable objects, or that you just send the objects to the other guild and no longer have access to them. So that's why the guilds are pretty different from what we've seen out there, but it seems really interesting.
Cool, thanks.
Cool. So any other questions, or I'm done?
Hello, I wonder if by coding, you can say to your software to use one thread or the other, or to use one processor or the other, and doing the management by code.
Yes-ish. Actually, you can do that with Ruby. That's when I have, like, can I go really fast to the first slide? No. Okay, when I was talking about the possibilities for doing concurrency in Ruby, I was saying threads, processes. The one that you're describing is called fibers. So a fiber is basically a context that runs within a thread, and you can switch between them manually. So you know when one is running, on the other one is running. So you can have that kind of concurrency where you know precisely how fibers are cooperating in the same thread. So Ruby actually allows you to do that if you want to. Yeah.
Thank you.
Cool. No more questions? Snack time.
Exactly. So we have 15.